Hi, in today's video, we're going to talk about coupled oscillators and normal modes. So whenever you combine two or more than two oscillating systems together, then you end up getting a coupled oscillator. Coupled oscillators are quite interesting because even though the nature of their motion is not necessarily harmonic, not necessarily sinusoidal, it can be represented as the superposition of distinct sinusoidal frequencies. And these sinusoidal frequencies, which are hidden within the general solution of coupled oscillators, can be extracted by studying what are known as normal modes and normal frequencies. So normal modes are those setups in which the entire coupled oscillator executes simple harmonic motion, which is only possible for few restricted initial conditions. So in this video, first of all, what I'm going to do is I'm going to discuss these ideas of coupled oscillators by taking a very simple example of a 2-mass 3-spring system. So in this particular setup, first of all, I'm going to obtain the equations of motion. And from the equations of motion, I'm going to obtain the general solution. And I'm going to show how the general solution of this kind of a coupled oscillator can be written as a linear superposition of distinct frequencies. And I'm going to obtain those distinct frequencies by looking at normal modes, these configurations in which the entire setup will execute SHM, and the frequencies associated with them, which are normal frequencies. And I'm also going to discuss normal coordinates, which are those combinations of the coordinates that executes SHM. All right. And finally, I'm going to look at a very specific situation of the general solution in which the coupled oscillator exhibits beats, in which one point mass exchanges energy with the other point mass slowly over a period of time. So let us begin. Alright, so what we have here is a system of 2 point masses. So the first point mass, let's suppose its mass is m, is connected to a spring which has a spring constant of k, let's suppose, which is attached to the fixed ceiling or a wall on the other end. And this mass is attached to another spring, let's suppose it has a spring constant of k dash, which is attached to another point mass, let's suppose it has the same mass m. And this mass m is on the other hand attached to another spring having a spring constant, let's suppose k, whose other end is attached to some kind of a wall. Now, let's suppose the first diagram is the diagram of equilibrium, in which the entire system is at rest and the springs have their equilibrium lengths associated with it. However, if I displace these 2 point mass by some kind of a distance so that there is a net effective displacement created in the springs compared to its equilibrium lengths, then the entire system starts executing motion. So let me say that the first mass is displaced by an amount of x1 and the second mass is displaced by an amount of x2. Here I am considering that this is the x-axis. All right, so the entire motion is going to be along the x-axis. It is restricted to 1 dimensions. So x1 and x2 here are the variables, which are the instantaneous displacements of mass m and m for the first and the second mass respectively. And if we can create some kind of equations of motion which governs how x1 and x2 varies with time, and from there we can understand how the motion is going to take place. So to do that, I'm going to apply the Newtonian approach. So let me write the force equation for the first and the second mass. So the force equation is simply the Newton's second law, which says that whatever net force is acting on a given mass at any given point in time results in the acceleration experienced by that particle at that instant. All right. So let's suppose first we look at the first mass. So the first mass has a mass m and its acceleration is restricted to the x-axis, and I'm defining its instantaneous coordinate to be x1. So its acceleration is x1 double dot. So x1 double dot simply represents the second order derivative of x1 with respect to time. All right. Now, what is the net amount of force experienced by the first mass? The net amount of force experienced by the first mass is associated with the first spring as well as the second spring, right? So what is the extension experienced by the first spring? The extension experienced by the first spring is x1. So the force associated with that is kx1. And since the force is acting opposite to x1, I'll have to write minus kx1. Quite simple. Now, what about the extension experienced by the second spring? Now, the second spring is different from the first spring in the sense that in the second spring, both the ends are experiencing some kind of an extension. So the overall extension experienced by the second spring can be simply given as x1 minus x2. So x1 minus x2 will give us the extension of the second spring compared to its equilibrium. And since the spring constant of the second spring is k dash, I write the force as k dash x1 minus x2. Now let's suppose if x1 is greater than x2, in that case, the direction of force is opposite to the extension that is created. In that sense, I'll apply a negative sign here, and this gives us the force equation for the first mass. So the force equation for the first mass is x1 double dot plus kx1 plus k dash x1 minus x2 is equal to 0. This is the force equation for the first mass. Similarly, we can also obtain the force equation for the second mass. All right. So the force equation for the second mass is, if the second mass has an instantaneous displacement of x2, then its acceleration is x2 double dot. Now, the second mass will be affected by the extensions of the second spring as well as the third spring. If we are only looking at the force due to the third spring, then the extension in the third spring is given by x2, right? And since its spring constant is k, the force is kx2. And since this is acting opposite to the direction of x2, so x2 is in this direction, the force will be acting in the opposite direction. So I apply a negative sign here. And the second force is due to the middle spring, which causes an extension of, let's suppose, x2 minus x1, and it has a spring constant of k dash. So now if x2 is greater than x1, in that case, the force is again opposite to x2. So I apply a negative sign here. So the force equation for the second mass comes out to be mx2 double dot plus kx2. Here I'll have to write kx dash x2 minus x1. So if I write minus, this simply becomes kx dash x1 minus x2 is equal to 0. So these are the two force equations corresponding to both these two masses. Let's suppose I name these point number 1 and point number 2. Now, if I am interested in finding out the solutions for x1 and x2 from here, what I'm going to do is I'm going to apply a couple of tricks. So first of all, I'm going to add these two equations 1 and 2, and this is going to help us in obtaining the solutions for x1 and x2. This gives us mx1 double dot plus kx1 plus mx2 double dot plus kx2 plus k dash x1 minus x2 minus x1 plus x2 is equal to 0. Here x1, x1, x2, x2 gets cancelled. So I am left with the equation m x1 double dot plus x2 double dot plus k x1 plus x2 is equal to 0, or finally I have x1 double dot plus x2 double dot plus k upon m x1 plus x2 is equal to 0. Now some of you may be familiar with this kind of a differential equation. This is simply the differential equation corresponding to some kind of a sinusoidal solution, or this kind of a system usually gives us simple harmonic oscillations, but for the variable x1 plus x2. So let me write it in different manner. So if I have a second order derivative of the variable x1 plus x2 plus k upon m x1 plus x2. So this is a second order differential equation with respect to the variable x1 plus x2. Can you see that? And the standard solution for this kind of a differential equation can simply be written as x1 at a time t plus x2 at a time t can simply be written as, let's suppose, cos omega t plus d sine omega t, where omega is simply equal to root over k upon m. All right, I am sure that you must have seen differential equations of this form that give this kind of a standard solution. Now here the entire solution of x1 plus x2, okay, these are not the solutions individual of x1 and x2. This is a solution of x1 plus x2 is c cos omega t plus d sin omega t, where omega here is the frequency root over k upon m, and the sum of cos omega t and sin omega t basically can be written as some kind of a sinusoidal function. So let me show you that this expression is very much equivalent to 2a1 cos omega t plus phi 1. Okay, I can write this expression and this expression in the same manner. Let me show you how. So if I have some expression of 2a1 cos omega t, omega 1 t plus phi 1. So here let's suppose instead of this being omega, this is omega 1, okay, because I'll get another omega later on. So let's suppose this is omega 1. In this case, if you look at this particular expression, why I've written 2, this will also become clearer in just a moment. So 2a1 cos omega 1 t plus phi can be written as cos a plus b. Okay, what is cos a plus b? So this is nothing but 2a1 cos a plus b is cos omega 1 t cos phi 1 minus sin omega 1 t and sin phi 1, right? So this is equal to 2a1 cos omega 1 t. Now what is cos phi 1? So phi 1 here is just some kind of a constant. Here phi 1 and a1 are constants, okay? These all depend upon the initial conditions of the given system. So this constant can be written as maybe something like b1, okay, and again minus 2a1 sin omega 1 t, and again sin phi 1 is another constant, so which can simply be written as, let's suppose, b2. So these constants being multiplied can be written as, let's suppose, another constant c cos omega 1 t, while minus 2a1 b2 can be written as some constant, let's suppose d sin omega 1 t, which is nothing but this particular expression, right? This is the same. So c cos omega 1 t plus d sin omega 1 t is the same as, let's suppose, 2a1 cos omega t plus phi 1. Here capital C and capital D are some constants, and capital A1 and phi 1 are also some kind of a constant that depends upon the initial configurations. And if we want, we can find out the relationships between CA1 and D phi 1, but that's not necessary here. The reason I've written both these two expressions is because I may use one of these expressions depending upon what I'm discussing. So we have obtained the solution for x1 plus x2, right? Now let me do one more thing. Here I've added equations 1 and 2. Let me subtract equation number 2 from equation 1 and see what we get. So if we subtract equation number 2 from equation 1, then I'll simply get the expression that mx1 double dot plus k of x1 minus mx2 double dot minus k of x2 plus k dash x1 minus x2 plus x1 minus x2, which is equal to 0. So this equation can be simplified as mx1 double dot minus x2 double dot plus k x1 minus x2 plus k dash. If I take 2 out of it, it becomes x1 minus x2 because there is 2x1 minus 2x2, right? Which is equal to 0. This can be simplified as mx1 double dot minus x2 double dot plus k plus 2k dash x1 minus x2 is equal to 0, which can be further simplified as x1 minus x2, its second order derivative with respect to time, plus k plus 2k dash upon m x1 minus x2. Now this is the same standard differential equation of x1 minus x2 with respect to time as was this one, and it has a similar kind of a standard differential equation solution. So the solution of x1t minus x2t is simply equal to some kind of a constant e cos omega 2t plus f sin omega 2t, where e and f, these are just constants that depend upon the initial conditions, where omega 2 is simply equal to k plus 2k dash upon m root over. Okay, so the omega 2 is just equal to root over k plus 2k dash upon m. This can, in a similar fashion as I showed you here, can also be written as just some kind of a sinusoidal variation. Let's suppose 2a2 cos omega 2t plus phi 2. Here the constants are the phase phi 2 and the amplitude a2. So as you can see, the difference of these coordinates x1 minus x2 and the sum of these coordinates x1 plus x2 both have sinusoidal variations. Now this is something very interesting that I'm going to come back to later on. These coordinates are given a very special name. It is called normal coordinates. You see, the individual point masses may not necessarily execute simple harmonic oscillations, but a linear combination of these coordinates may execute simple harmonic oscillations. And these linear combinations of the coordinates, that is x1 plus x2 and x1 minus x2, are known as normal coordinates. But before I come to normal coordinates, let me use these expressions. Let's suppose this is point number 3 and point number 4 to obtain a general solution for x1 and x2 separately. Again, I can do that by, let's suppose, adding point number 3 and 4. So if I add point number 3 and 4, that is x1 plus x2 and x1 minus x2, what do I get? So x1 plus x2 plus x1 minus x2, this simply gives us, point number 3 is 2a1 cos omega 1t plus phi 1, and point number 4 contains plus 2a2 cos omega 2t plus phi 2. So this is nothing but, if you cancel out the x2 here, it simply becomes 2x1. So 2x1, the 2 and the 2, these gets cancelled, and we are left with x1t is equal to a1 cos omega 1t plus phi 1 plus a2 cos omega 2t plus phi 2. This is quite interesting. We have obtained the general solution for the first mass. Now let us quickly do a subtraction of point number 3 from 4, or rather point number 4 from 3. So what I'm going to do is x1 plus x2 minus x1 minus x2, which becomes x1 plus x2, is simply equal to 2a1 cos omega 1t plus phi 1 minus 2a2 cos omega 2t plus phi 2. Here again, the x1 cancels out, right? And you're left with 2x2. The 2 gets cancelled on both hand sides. And finally, you end up getting x2t is equal to a1 cos omega 1t plus phi 1 minus a2 cos omega 2t plus phi 2. So this is the general solution for the second mass. Now it's interesting, let us just do a little bit of a discussion of these two expressions. So this is, let's suppose, point number 5 and point number 6. So we have obtained the general solution for both these two masses. So if you look at this system, both the masses, the first mass and the second mass, is experiencing some sort of an oscillation. And whatever nature of oscillations these two masses are expressing can be mathematically written using these two expressions that we have just now obtained. x1 is a1 cos omega 1t plus phi 1 plus a2 cos omega 2t plus phi 2. And x2 is a1 cos omega 1t plus phi 1 minus a2 cos omega 2t plus phi 2. Here, these expressions that you see, that is a1, a2, these are just some kind of a constants that depend upon the initial conditions. Similarly, the phases that you see phi 1, phi 2, these are also constants that depend upon the initial conditions. However, the omega 1 and omega 2, these are some distinct frequencies, right? We already showed that omega 1 is equal to root over k upon m, while omega 2 is root over k plus 2k dash upon m. So these are distinct frequencies. Both omega 1 and omega 2 are distinct frequencies. So what you see here is that the general solution of the coupled oscillator is actually a superposition of two distinct frequencies. You see, the general solution of x1 is a superposition of these two distinct frequencies, while the general solution of x2 is a superposition of these two distinct frequencies. Now, x1 and x2 are not necessarily executing some sinusoidal variation, but they're executing some kind of a motion that can be represented by the linear superposition of two distinct sinusoidal frequencies. Now, what are these frequencies? These frequencies are known as normal coordinates. To appreciate these frequencies better, let us discuss two very specific scenarios in which the entire system will exhibit either one frequency or the other frequency. So to do that, we'll consider two special cases. So let us take a look at that. So we'll start with the normal modes and normal coordinates. So let us discuss two very interesting configurations in which when we provide some kind of initial condition to the coupled oscillator system, then the entire oscillator is going to exhibit simple harmonic oscillations. So the first case is when we provide some kind of an initial condition such that the constant A2 comes out to be 0. Alright, so if we provide some kind of an initial condition where the constant A2 comes out to be 0, let's suppose, if we are able to create a setup where the constant A2 comes out to be 0, in that case, both the systems x1 and x2 are going to oscillate with the same frequency omega 1. So in that kind of a situation, both x1 and x2 are going to exhibit some kind of a sinusoidal variation with frequency omega 1 and constant phase difference phi 1, as you can see from the equation here. Now, what does this kind of a configuration represent? Let me draw a diagram and explain it to you. So here you see we have this simple schematic which represents that situation in which it is possible to find a set of initial conditions where the second constant A2 goes to 0 such that now both x1 and x2 oscillates with the same frequency and the same constant phase difference. This represents what is known as the normal mode. So here, as you can see, both these two masses are oscillating in this kind of a manner. All right, so if I give equal displacements to both the masses in the same directions, then what is going to happen is that both the masses are going to oscillate in this kind of a fashion. So as you see here, this inner spring is unstretched. This inner spring is unstretched and both the masses and their extensions associated with x1 and x2 are in phase and exactly equal at any given point in time. They are both oscillating with the same frequency and the same constant phase difference of 0. This is known as the first normal mode. The first normal mode is characterized by the entire system executing simple harmonic oscillations of same frequency and a constant phase difference of 0 and same amplitude. As is quite evident from the equation, the frequency is the angular frequency of omega 1 is the root over k upon m. So as you can see, it is only the spring constant of the outer springs that is contributing towards the angular frequency and not the spring constant of the inner spring, because the inner spring remains unstretched due to this kind of a motion. So the normal mode is in generally defined as that kind of a state of coupled oscillators in which under specific initial conditions the entire system starts executing simple harmonic oscillations of a distinct frequency. Now, the other kind of a configuration is also possible. If we can give some kind of an initial condition where A1 comes out to be 0, in that case, you can see from the general solution that if A1 comes out to be 0, only the second two terms are left. The second term is just A2 cos omega 2t plus phi 2. So x1t is basically equal to minus x2t, which is nothing but A2 cos omega 2t plus phi 2. Yes, x1t is just equal to x2 or minus x2, which is equal to A2 cos omega 2t plus phi 2. Here there is some kind of a constant phase difference phi 2 and a constant frequency of omega 2. So under those situations where capital A1 constant is 0, both the configurations will oscillate with the same frequency but because there is a minus sign here, both of them will be out of phase with respect to each other by, let's suppose, 180 degrees. Let me draw a schematic to show you the motion that can be visualized. So here we have the schematic for the second normal mode. So here, as you can see, the configuration is such that if you displace the entire setup in such a manner that you displace the first mass by a certain amount and the second mass by the same amount but in the opposite directions, the oscillations that you end up getting is something like this. See, both the two masses will be exhibiting the same frequency with a constant phase difference of 180 degrees. That means if one mass is going outwards, the other mass is going outwards in the opposite direction, and then both the masses are coming towards each other, going away from each other, towards each other, going away from each other. At every point, their amplitudes are same and they're oscillating with the same frequencies, but they are out of phase by 180 degrees. So as you can see here, if one mass is, let's suppose, going to the right with some kind of a displacement of x2, the other is going towards the left with some kind of a displacement x1, where the magnitude of x1 and x2 are exactly equal, but they are directed in opposite directions. So this is known as the second normal mode. So in the second normal mode, what you end up getting is you have the same frequency with which the system is oscillating, or all the points in the system is oscillating. That is, omega 2 is equal to k plus 2k dash upon m, but the amplitudes are equal but out of phase by 180 degrees. So these are two distinct configurations which are possible in this kind of a coupled oscillator setup when the entire system will execute simple harmonic oscillations of a distinct frequency. One is the setup where the entire system is oscillating with respect to a frequency omega 1 in phase. Other is the setup in which the entire system is oscillating with the same frequency omega 2 but out of phase. Now this must be kind of obvious to you that this configuration is possible when I provide some initial displacement to x1, that is, let's suppose some displacement a2, and initial displacement to x2 that is equal to minus a2, and I provide zero velocities to x1 and x2 at time t is equal to 0. So under these initial conditions, both the masses will be exhibiting distinct frequencies different from each other. Now, why are normal modes important? Normal modes are important because they reveal to us that there are distinct frequencies in that particular setup. Because the general solution, as it turns out, is a linear superposition of these distinct frequencies. So if you remember the general solution here, the general solution is a linear superposition of these distinct frequencies. This is the one frequency, this is the other. This is the one frequency, this is the other. So whenever you deal with coupled oscillators, even though it may be a very complicated looking coupled oscillator, in our case we have taken a very simplistic coupled oscillator, but you may have coupled oscillators with many number of masses. But if you are able to find out the normal frequencies associated with the normal modes, then it just so happens that the general solution is usually a linear superposition of those distinct frequencies. Therefore, these frequencies are given the name of normal frequencies. So this coupled oscillator has two normal frequencies. It has 2 degrees of freedom and 2 normal frequencies and 2 normal modes, which brings me to something that I derived just some moments back. These quantities x1 plus x2, you remember? This x1 plus x2 is a quantity that is also oscillating with a one frequency omega 1, while x1 minus x2 is something that is oscillating with frequency omega 2. So it is also something unique in these kind of coupled oscillators that the general solutions may not exhibit SHM, but we can find certain kinds of linear combinations of those general coordinates. In this case, I have x1 plus x2 and x1 minus x2, which will have some kind of a sinusoidal variation of a fixed frequency. So this is kind of interesting, isn't it? the general coordinates will exhibit SHM only under very particular initial conditions, not always. It is usually a linear superposition of the frequency, but we can find linear superpositions of the coordinates that will exhibit some kind of a sinusoidal variation. These coordinates are given a special name. They are known as normal coordinates. So normal coordinates are those coordinates, or rather they are the linear combination of the coordinates of the masses that at all times will undergo some kind of a sinusoidal variation, and the frequency associated with those coordinates are known as normal frequencies. And these normal frequencies can be physically visualized when we give such initial conditions that the entire system starts exhibiting one or the other normal frequency, and these states are known as normal modes. So this is all very, very interesting. Now, I want to, before I end the video, show something very unique about the nature of the motion of the system. The system is moving in such a manner that these masses are not necessarily executing simple harmonic oscillations, but they are exchanging energy with respect to each other. And I can show that by looking at the beats exhibited by these coordinates. Let me give some kind of an initial condition to the entire configuration such that x1 at time t is equal to 0 is, let's suppose, 0. That means the first mass is not displaced. And x2 at time t is equal to 0 is, let's suppose, I give it some kind of an initial displacement. Let's suppose capital A. I do not provide them any velocities at time t is equal to 0. So x1 dot and x2 dot at time t is equal to 0 is 0. Under such initial configuration, what is the nature of the general relationship? That is what I want to look at. So here are the general solutions that we have already obtained, and I want to find out the values of the constants involved based on these initial conditions, because I want to show a very interesting phenomena that happens in this motion. But I would be more comfortable with the expression that involves the sines and the cosines both. So I showed just some time back that an expression of the form a cos omega t plus phi can be written as, let's suppose, some constant a cos omega 1 t plus some constant b sine omega 1 t. Just some time back I showed to you that both these two expressions are kind of equivalent to each other. So I'm going to use that expression just because I would feel more comfortable solving the constants there. So the first expression can be written, let's suppose, with respect to constants small a and small b. And the second expression also, I would like to write it in this fashion. Let's suppose this is simply equal to c cos omega 2t plus, let's suppose, some constant d sine omega 2t. Here also c and d are constants. Similarly, the expression for x2 can also be written as a cos omega 1t plus b sine omega 1t minus c cos omega 2t minus d sine omega 2t. So I want to find out what these values a, b, c, d are after applying these initial conditions. So let us apply that and see what we get. So at time t is equal to 0, what does x1 become? x1 simply becomes 0, because x1 at time t is equal to 0 is 0, is equal to a cos 0 plus b sine 0 plus c cos 0 plus d sine 0. Here, of course, the sine terms vanishes and we are left with simply a plus c is equal to 0. This is one equation we have. Similarly, let us apply it to x is equal to 2 equation, and if I apply it to x is equal to 2 equation, I simply get 0 is equal to a cos 0 plus b sine 0 minus c cos 0 minus d sine 0. Again, here the sine terms vanishes and I am left with a minus c is equal to 0. Sorry, I made a mistake. x2 was equal to a. x2 was not equal to 0. x2 was equal to a. So this must be equal to a. So this must be equal to a. So here in this equation, if I apply the fact that a is equal to minus c, so this simply gives us minus c is equal to a, or c is equal to minus a upon 2 and a is equal to minus a upon 2, which is a upon 2, a as in capital A. So we have found out the constants, the small a and the small c. Now we have to find out the constants b and d. To find out the constants b and d, what I'm going to do is I'm going to do the time derivative. That is, I'm going to look at the velocities. So if I'm interested in finding out the velocities, I can find out what is x1t dot and x2t dot. Okay, so x1t dot I can obtain from this expression as a omega 1 minus sine omega 1t, right? And b omega 1 cos omega 1t and minus c omega 2 minus c omega 2 sine omega 2t, and we finally have plus d omega 2 cos omega 2t. Similarly, for x2 dot, I will end up getting minus a omega 1 psi omega 1t plus b1 omega 1 cos omega 1t minus plus c omega 2 sine omega 2t plus, or rather minus d omega 2 cos omega 2t. Now what happens to these values at time t is equal to 0? x1 dot at t is equal to 0 and x2 dot at t is equal to 0 is 0. So from here I will get at time t is equal to 0, this 0 is equal to minus a omega 1 sine 0 plus b1, no sorry, this is just b, not b1, b omega 1 cos 0 minus c omega 2 sine 0 plus d omega 2 cos 0, right? Again, the sine terms vanishes and we are left with b1 omega 1 plus, sorry, it's just b, not b1, b omega 1 plus d omega 2 is equal to 0. Similarly, for the second equation, what do we get? 0 is equal to, at time t is equal to 0, minus a omega 1 sine 0 plus b omega 1 cos 0 plus c omega 2 sine 0 minus d omega 2 cos 0. This here also the sine terms vanishes and I am left with b omega 1 is equal to d omega 2. So this is one equation and this is the other equation. So if I apply this equation to the first equation here, this simply becomes b omega 1 plus d omega 2 is equal to b omega 1, right? So this is 0, or b omega 1 is equal to 0. Omega 1 is clearly not equal to 0. We know that. We end up getting b is equal to 0. And if b is equal to 0, then from this expression I can immediately say that d is also equal to 0. So I end up getting b is equal to 0, d is equal to 0, and a is equal to a by 2, and c is equal to minus a by 2. If I put these back in our original expressions, in these expressions, the nature of the equations look something like this. So finally, these are the solutions of x1 and x2 when we provide them with this kind of an initial setup where we only displace the second mass by some kind of a fixed amount. That's it. So when we displace the second mass by some kind of a fixed value, capital A, then the solutions become this. Now, as you can see, this is again some kind of a linear combination of distinct frequencies omega 1 and omega 2. Now, before I show you what is the nature of the motion under this kind of a configuration, let me sort of do some trigonometric substitutions here to one of the expressions, just so that you can appreciate the results that we will finally obtain. So what I'm going to do is I'm going to substitute omega 1 with, let's suppose, half of 2 omega 1, which is just equal to half of omega 1 plus omega 2 plus omega 1 minus omega 2. That can simply be written as omega 1 plus omega 2 divided by 2 minus omega 2 minus omega 1 divided by 2. Similarly, I'm going to substitute omega 2 with half of 2 omega 2. That can simply be written as half of omega 2 plus omega 1 plus omega 2 minus omega 1. So this is equal to omega 2 plus omega 1 upon 2 plus omega 2 minus omega 1 upon 2. So as you can see, I have written omega 1 in terms of this particular frequency, which is the average of both the frequencies, and this, which is the average of the difference of both the frequencies, and omega 2 also as a sum of the average of both the frequencies and half of the difference of both the frequencies here. Now, why am I doing this? You'll just discover it yourself. Let me substitute these two expressions in, let me do it for x1 and then it will become obvious for x2. So let me do it for x1, and then this final solution for x1 simply transforms into cos omega 1t can be written as cos omega 1 is nothing but omega 2 plus omega 1 upon 2 t minus omega 2 minus omega 1 upon 2 t, right? And minus cos omega 2 t can be written as omega 2 plus omega 1 upon 2 t plus omega 2 minus omega 1 upon 2 t. Now, what is cos a plus b and cos a minus b? Well, it is nothing but the expression here. So according to this, if I write down the entire expression, then this simply becomes cos omega 2 plus omega 1 upon 2 t cos omega 2 minus omega 1 upon 2 t. Then I'll end up getting plus sine omega 2 plus omega 1 upon 2 t sine omega 2 minus omega 1 upon 2 t for the first expression. And for the second expression, I'll simply get minus cos omega 2 plus omega 1 upon 2 t cos omega 2 minus omega 1 upon 2 t, and minus minus plus sine omega 2 plus omega 1 upon 2 t and sine omega 2 minus omega 1 upon 2 t. Now you might be wondering why we are doing this. I'll come to the results in just a moment. Okay, so this is a term and this is a term that, no, sorry, not these two terms, but rather this term and this term, they are the same but opposite, so they get cancelled out. And finally, we are left with these two terms which are exactly the same. Okay, so these two terms are exactly the same. So twice of a by 2 simply becomes a, and sine omega 2 plus omega 1 upon 2 t and sine omega 2 minus omega 1 upon 2 t is just the solution x1t. Okay, this is just a solution x1t. I can obtain a similar solution for x2t also, but let me first show you the graphical representation of what this kind of an expression actually means. Okay, so here we have the graphical representation of both x1 and x2 for the initial conditions that I have provided here. Okay, for these initial conditions, how does x1 and x2 vary with respect to time? So let us try to study this and see what sort of a peculiar behavior we can understand. So x1 here is varying with respect to time, which is here in the y-axis. Okay, and x2 is varying with respect to a time. All right, now what sort of information can we get from these graphical representations? So x1, so let us first look at x2. So if you look at the initial conditions, we only provided some displacement to x2. We did not give any displacement to x1. We did not give any velocities to x1 and x2 at time t is equal to 0. We only gave some kind of an initial displacement to x2. And because we gave some initial displacements to x2, you can clearly see that x2 starts oscillating. But as it oscillates, its amplitude of oscillation decreases. So x2 starts oscillating, but with time its amplitude starts decreasing, and after some time its amplitude again starts increasing, and after some time it again starts decreasing, and after some time it again starts increasing. So the system of x2 is oscillating, its amplitude decreasing, and after some time its amplitude increasing, and after some time its amplitude decreasing, and after some time its amplitude increasing, and on and on. And because x1, the first mass, is connected to x2, what you see for the first mass is that x1 starts oscillating with increasing amplitude, which decreases after some time, with increasing amplitude, which decreases after some time. So initially the x1 is at rest, but when we provide displacement to x2, because it's connected to x2, the x1 also starts oscillating. Its amplitude increases, it reaches a maximum, and the amplitude decreases, becomes minimum. Again the amplitude increases, becomes maximum. Again the amplitude decreases, becomes minimum. So the behavior of both the masses is such that when I displace x2 from its initial configuration, it starts oscillating, amplitude decreases. At the same time, x1 starts oscillating, its amplitude increases. And after some time, x1's amplitude decreases and x2's amplitude starts increasing. So two very interesting things are happening here. The first interesting thing is that what we just now derived, this frequency, omega 2 plus omega 1 and omega 2 minus omega 1, these are the two frequencies that you can see here. The frequency of the oscillation of x1 and x2 and the frequency of the modulation with which this wave is happening. These are these two frequencies. So the frequency with which the oscillations are happening, that is nothing but omega 2 plus omega 1 upon 2. The frequencies at which the oscillations are happening, that is omega 2 plus omega 1 upon 2. But the frequency angle at which the modulation is happening, you see the amplitudes are modulated. Amplitudes are slowly increasing and the amplitudes are slowly decreasing. The frequency with respect to this modulation that is happening to that original oscillations, that is omega 2 minus omega 1 upon 2. So a graphical representation of the general solution for our initial conditions provides these beats that you have these oscillations, but these oscillations are being modulated by a further oscillation. Right? You have these oscillations, but these oscillations are being modulated by a further oscillation. And the oscillations are happening with this frequency and they are being modulated by this particular frequency. So as you can see, this is the sine 1 frequency and the sine another frequency term. Similarly, the same thing is also true for the x2 case. It is also oscillating and these oscillations are being modulated by a further oscillation. All right, so this is very interesting that when we only give one displacement to one of the masses, that since that mass is connected to the first mass, they both are oscillating with a particular frequency which gets modulated by another frequency. And what's more interesting is that both of them are exchanging energy with respect to time. So as you see, as the first mass increases in amplitude, the second mass decreases in amplitude. And when the first mass reaches maximum, the second mass amplitude becomes minimum. As the second mass amplitude increases, the first mass amplitude decreases. And when the second mass amplitude becomes maximum, the first mass amplitude becomes minimum. After some time, the first mass amplitude increases, the second mass amplitude decreases. So when the first system is oscillating at its maximum amplitude, the second system is at rest. And when it starts losing energy, the second system starts gaining energy and it reaches a maximum amplitude. And after some time, the second mass starts losing energy and the first mass starts gaining energy and reaching maximum amplitude. And this starts losing energy and this starts gaining energy. So this keeps happening over and over again. This loses energy, this gains energy. This loses energy, this gains energy. And both these two subsystems in the coupled oscillator are sort of oscillating by exchanging energy from one to the other, from the one to the other, and on and on and on. So this is quite interesting to see. All right, so that is all for today's class. I hope you enjoyed and learned something from the sort of lecture. Let me do a very quick revision. We took the case of a coupled oscillator where there are two masses and three springs attached together, and the outer springs are connected to two walls. We obtained the force equations using the Newtonian approach. From there, we obtained two differential equations that can be solved. And when we did that, we found out that there is a coordinate called x1 plus x2 that is executing simple harmonic oscillations or sinusoidal frequencies. And there is another coordinate x1 minus x2 that is executing simple harmonic oscillations of constant frequency. And I said that these are known as normal coordinates. From there, I obtained the general solutions. The general solutions are nothing but linear superpositions of two distinct frequencies, omega 1 and omega 2. From here, I talked about normal modes, that if I provide certain initial configurations to both the systems, they can exhibit simple harmonic oscillations of distinct frequencies. So this is the first normal mode and this is the second normal mode. And then we talked about when we provide one displacement to one of the masses, then the nature of the motion is such that that mass will start oscillating, but it will keep on losing energy over time, while the other mass will start oscillating and keep on gaining energy over time. And this kind of an oscillation is modulated by a further oscillation, and the values are omega 2 plus omega 1 by 2 and omega 2 minus omega 1 by 2 respectively. So that is all for today. Thank you very much.